This chapter is divided into two parts. This is part one, where we do basic definitions, basic properties. Much of this we've already covered in class, so it will be a review for most of you. Starting from the definition, if I have a group and an element of the group, there may or may not be some power of that element that results, positive power of the element that results in the identity. If it happens, then we say A has finite order, and we define the order of the element to be the smallest positive integer, which, when put into the exponent, results in the identity. The notation we use is the notation that we were using before when we defined this in the context of the group of the symmetric group on n objects. The order of the element is n if and only if a to the n is the identity, and n is the smallest such integer, positive integer. And here's where we have something new. This was not possible in a finite group like the group of symmetries on n objects. It's possible that a to the n is not the identity for any positive integer n. And when this happens, we say A has infinite order. So let's just practice a little bit using this definition. I would like you to compute the order of -1 in the group of integers under addition. Notice this is an additive group, and so you're going to have to translate the definition of order of an element into additive notation. Make sure you do that before you answer the question. And then the second is to look at the order of -1 now as an element of the non-zero reals. In this case, the group is a group under multiplication. Try those yourself, pause your video, and once you have the answer, you can return to the video. We will discuss the answer to each of these questions. So first one, what is the order of -1 in the group of integers? Well, as we mentioned before, it's an additive group. So when we talk about the order, instead of looking at x to the k being the identity, we're looking for the smallest positive integer k, so that when I multiply k times x, I take x plus x plus x k times, I get the identity in the additive group, which we usually denote by 0. So I want to find the smallest positive integer k such that k times x is 0. Well, when I'm interested in the order of -1, I would need a positive integer k, so that k times -1 is 0. Clearly, there is no such positive integer, and therefore we conclude that -1 has infinite order in this group. On the other hand, when we're looking at the multiplicative group of non-zero reals, I want, again, a power of -1 that gives me 1. Clearly, if I take -1 squared, that gives 1, which is the identity in that group. And again, it's obvious that no smaller positive exponent will give you 1, so we conclude the order of -1 is 2 in the multiplicative group of non-zero reals. Notice that the group here is an infinite group. It can have elements of finite order. On the other hand, if you have a finite group, there is no possibility of an element of infinite order. Some basic properties of order of an element. First of all, if I have the identity, clearly its order is 1. And on the other hand, if I know that the order of my element is 1, a to the 1 is the identity, that says a is the identity. So we conclude that order of a is 1 if and only if a is the identity. Very straightforward, and it says that the only element in your group of order 1 is the identity. This next property is very useful and not difficult to prove, so I would like you to pause the video, see if you can prove this for yourself. Use the definition of order, and see if you can show that the order of A is the order of A inverse. Once you have proven it, then you come back to the video and we'll go through the proof. Let's look at this order of A and the order of A inverse. We want to show that they're the same. So let's start by giving a name to the order of A. We call it n. Well, what does that tell you? It says that if I take a, raise it to the nth power, I get the identity, and n is a positive integer. Furthermore, what it says is that if I take a to any other power, positive integer but less than n, I don't get the identity. This is really what the definition of finite order tells you. So let's take minus 1. We're interested in the order of a to the minus 1. So let's look at a to the minus 1, raise it to n, the order of a, and see if we get the identity. Using the properties of the exponent, I can see that a minus 1 to the n is a n to the minus 1. We've talked about those properties before. What does that tell you? It says that the order of a inverse is at most n. It doesn't tell you the order of a inverse is n. All it says is that when I take a inverse, raise it to the nth power, I get the identity. The order of a inverse is the smallest positive integer that does that. So the order must be less than or equal to any other positive integer that has this effect. We need to show that this inequality is actually equality. So let's look at the order of a inverse and give it a name. We call it k. What do we know about k? I know that if I take a inverse and raise it to the kth power, I get the identity. Again, using my properties of the exponent, that tells me that a to the k inverse is e. Well, if a to the k inverse is e, then that guarantees to me that a to the k is e as well. Now, let's think about what this means. I've taken a, I've raised it to a positive integer power, I get the identity. Now, the order of a is the smallest positive integer that does that. K does it, and therefore the order of a must be less than or equal to k. So order of a inverse greater than or equal to n, the order of a. Now, if I look at these two inequalities, order of a inverse less than or equal to n, order of a inverse greater than or equal to n, I conclude that the order of a inverse is n, and of course being the order of a. This is what we wanted to prove. Now we know that the order of any element in the group and the order of its inverse are equal, which tells you, of course, if a is a finite order, so let G be a group and a an element of G, and this is a theorem that we proved previously. We showed that when G was the symmetric group on n objects, then when I had any element that was an exponent of a that resulted in the identity, then that exponent must be a multiple of n. The converse is true as well. The proof here relied on the division algorithm and the definition of order. It's really the same proof that we did before. The proof didn't depend on any properties of the symmetric group. So try it yourself, and when you're ready, come back to the video. Conditional statement that we want to prove, so we're going to start with the easier conditional statement. If I have a multiple of the order, then I take the a to that exponent k, then I should get the identity. Let's call order of a n and assume our hypothesis, assume that n divides k. That tells me that there's some integer q such that k is q times n. And let's see what happens when we take a and raise it to the qn power. Well, a to the qn power is then a to the n to the q. We're using our laws of exponents here. And a to the n, we know, because the order of a is n, a to the n is the identity. So I've taken a to the k. It is the identity, and that's really what I wanted to show. If the order of a is a factor of k, then a to the k is the identity. Now we need to look at the converse. The converse says, if I take a and I raise it to some power k, and I get the identity, then that exponent k must have been a multiple of the order. I'm going to, again, assign a name to the order. Order of a is n, and I assume my hypothesis. A to the k is the identity. Here's where we apply the division algorithm. I want to show that k is a multiple of n, so when I divide k by n, I get, in principle, a quotient, and a remainder. Now the remainder is an integer that is strictly less than n, my divisor, and greater than or equal to 0. Our goal here is to show that r is actually 0. I look at what I'm given. A to the k, is the identity e, and k, by my division algorithm, is k is qn plus r. So now I'm looking at this expression, a to the qn plus r, and I use the properties of exponents to rewrite it in this form. As before, a to the n is e, so now I'm looking at e to the q, which of course is the identity. The identity times a to the r is a to the r. Ultimately, what have I shown? I've shown that the identity is equal to a to the r. Okay, well, what does that tell you? Well, we know that r was less than n, and n is the smallest positive integer that appears as an exponent giving us the identity. A to the n is e, and no positive integer exponent can give us that. Because r is in this interval between 0 and n, the only integer in here that is not positive is 0. Consequently, we can conclude that r must be 0. N is the smallest positive integer such that a to the n is 0, a to the r is 0, therefore r is 0. Coming back to this expression here, k is qn plus r is 0, gives us what we wanted, k is equal to q times n. So we've proved that if a to the k is the identity, then n, which is the order of a, is a divisor of k. Up until now, we haven't really seen anything that we had not already seen when we were talking about the symmetric group. Let's look at what happens now if I have an element of infinite order. So I assume I have an element of the group of infinite order. What I can say then is that if I take powers of a, two powers of a to the I and a to the j, then those two elements in my group, a to the I and a to the j, will be equal if and only if their exponents are equal. By contrast, when I have an element of finite order, it is possible for two powers, ai and aj, to be equal, even if I and j are not equal. However, in this case, ai equals aj, if and only if that difference of the exponents is a multiple of the order. This is really the most important way in which elements of infinite order differ from elements of finite order. Let's look at the proof. So, two things to show. The first case, I'm looking at an element of infinite order, and I need to show that two powers are equal if and only if their exponents are equal. Assume I have an element of infinite order, and one direction is obvious. If I is equal to j, a to the I is a to the j. There's really not much to prove there. So let's look at the converse and assume that ai and aj are equal. Two different powers of a equal to each other. We'd like to show that the exponents are equal. I don't know I and j. I don't know anything about them, but I do know in general that if I have two integers, one of them must be greater than or equal to the other. So without any loss of generality, I'm going to call I the one greater than or equal to j. I multiply both sides of this by the inverse of a to the j, which is a to the minus j, and I get that a to the I times a to the minus j is the identity. And using my laws of exponents, that tells me a to the I minus j is the identity, and because of my assumption, I know that I minus j is greater than or equal to 0. Well, I had assumed that a had infinite order, and now I have an exponent that gives me 0. No positive exponent works, therefore I minus j must equal 0. That, of course, translates to the conclusion that I is equal to j. So if ai is equal to aj and a has infinite order, I must equal j. Finite order. Let's assume the order is n. And what we know from above is that AI is equal to AJ if and only if AI minus J is the identity. I just multiply both sides by A inverse. And I can recover AI equals AJ from this expression by multiplying both sides by AJ. The previous theorem that we showed said that if I take A to some power and I get the identity, that happens if and only if the order of A is a factor of the of that exponent. A to any exponent is the identity if and only if the order divides the exponent. Well, in this case, the exponent is I minus J. When I put these two statements together, AI equals AJ, equivalent to AI minus J's identity. AI minus J's identity is equivalent to N as a factor of I minus J, and then transitivity tells us that AI is equal to AJ if and only if N, which is the order of A, divides the difference of the exponents. Now, for those of you who have had number theory or are familiar with this notation, we can rewrite this by saying when A has finite order N, then 2 powers of A are equal if and only if their exponents are equivalent modulo N. This is the same as saying that N is a factor of I minus J. So we see that when we're dealing with an element of finite order, when we're dealing with the exponents, we're working modulo N. This is as if we're working in Z mod N. Let's practice a little bit with orders of elements in a finite group, a cyclic group in this case, because what we're interested in doing is trying to figure out what do I know about order of a power of A if I know the order of A. Now in this case I know the order of A is 12. That was the definition of my group. A to the 12th is the identity. A is a generator of this group, and so its order is 12. That tells me G is a cyclic group of order 12, and every element in G is of this form, A to some power. And what I'd like to do is to find the order of every element in this group, meaning I'm looking A to the K for each possible value of K between 0 and 11. Go ahead and write these out, try to find the order of every group. Remember now that we can use some of our results. We know that, for example, A to the K, or rather A and A inverse, have the same order. So if I am interested in finding the order of any element, if I already know the order of its inverse, I don't have to do any work. So try to do this as efficiently as possible, find the order of every element in G, and once you have, I would like you to look for patterns to see if you can guess how to write the order of A to the K as a function of K and of the order of A. Look at the result that you have, organize your information, and then see if you can guess a pattern. Once you've done that, come back to the video. If the order of A is or if K is 0, then the order of A to the 0 is 1. We've already established that. When K is 1, the order is 12. What happens when K is 2? I just take powers of A squared, and I find that the smallest power that gives me identity is 6. The order is 6. I do the same thing for A cubed, A to the 4th. Notice when we get to A to the 5th, the order is 12. I have to take 12 powers before I get back to the identity. Notice that tells me A to the 5th is a generator of my group. A to the 6th squared is the identity. That says the order of A to the 6th is 2. Now, I don't have to compute A to the 7th because I know that A to the 7th times A to the 5th, which is A to the 12th, is the identity. So I know A to the 7th has order 2. I know A to the 8th is going to have order 3, and so forth. In summary, here's what we have. Order of A0 is 1. Order of A1 is 12. Order of A2 and A10, these guys are inverses. A squared, A to the 10th. Multiply them, you get E. Therefore, they have the same order. A cubed, A to the 9th are inverses. They have the same order. Look for a pattern here. What do you notice? Certainly, if I take a squared, I get order 6. I'm thinking, well, order of a is 12. 12 over 2 is 6. I look at a cubed. 12 over 3 is 4. A fourth, 12 over 4 is 3. Now I get to a fifth. I can't divide 12 by 5. So here I have to stop and think for a little bit. What could this mean? Same with 10. Order of a to the 10 is the same as order of a squared. A to the 9th, same as order of a cubed. So I'm not just dividing 12 by that order. I have to divide 12 by something that is a divisor of 12, right? Because I have to get an integer for the order. So think about this. See if you can come up with a formula based on this information. In the next video, we will state that formula and we will prove it. And I hope that you have a conjecture of your own before you move on to the next part of Chapter 10.